Welcome back to MT3, Eigenvalues and Eigenvectors. Now this is part 2 of this series. It's quite a long set of topics I want to cover, so it's going to be split into a few parts. Alright, so far we have looked at what an eigenvalue problem is. We have proved that this is a bit of an untidy proof here, but we have shown that the eigenvalues of a Hermitian matrix or Hermitian operator are real. Yeah, so I'll put it operator or matrix are real. Now what I want to show is something equally important, which requires that particular result. I ended the last part by asking the question, what about the eigenvectors of a Hermitian operator? Can we say something about them? And the answer is yes, we can. And we're going to show this here. So we're going to prove that for a Hermitian operator A, the eigenvectors corresponding to different eigenvalues are orthogonal. Now this is the key phrase here, different eigenvalues. I will generalize this to all kinds of eigenvalues, but that proof will not be complete. Okay, so mathematically what we want to show is the following, is that if A hat is equal to A hat dagger, that is A is a Hermitian operator, then and if you have two such eigenvalue equations, A hat operating on xi is equal to lambda I xi, and this is the Dirac form, where I'm using the kets instead of the vectors xi, and we also have A hat operating on xj is equal to lambda j xj, where the lambda I is not equal to lambda j, so these are different eigenvalues. Then these two eigenvectors are orthogonal, so we must have the inner product of xi with xj is 0. Okay, so how do we show this? Well, let's give these two equations names or numbers. So this is equation 1 and this is equation 2. Alright, now let's see what we can do with it. So let's take equation 1 and take the Hermitian, the adjoint of Hermitian of equation 1. Take the adjoint of equation 1, and that gives us, so when we take the adjoint on both sides, so we have A hat xi adjoint is equal to the adjoint of lambda I xi adjoint. Now remember, when you take the adjoints, kets become bras, and of course the order of the terms gets reversed. So what we end up with then is this ket here xi becomes the bra xi, and this operator A gets an adjoint on it, and that's going to be equal to, now here we have a scalar lambda I, so the scalar gets this complex conjugated and the ket becomes a bra. Oops. Okay. The next thing we're going to do now is take the inner product of this thing with, so take the inner product with the ket xj. Alright, so this then becomes xi. Now let's see what happens to A hat dagger. So we know that we are given that this is a Hermitian operator, so A hat dagger is equal to A hat itself, so I'm going to change this back to an A hat. Then we have xj, and that's equal to lambda I. Now we also know that the eigenvalues of a Hermitian operator are real. Lambda I and lambda j, they belong to, that's from the previous proof. Alright, so this becomes real. So we can drop the complex conjugate, and then we have xi inner product with xj. Okay, so that gives us equation 3. Now what we do is we take equation 2, which is the eigenvalue equation for xj, and take the inner product on the left, so you're using the bra xi. You can see why I'm trying to do it, because I'm trying to get something which has this term on in both equations. So take inner product of 2 with xi, yeah, and that gives us xi a hat xj. That's going to be equal to, let's remind ourselves what this is. There's a lambda j here, which can just be pulled out of the inner product. It's anyhow it's a scalar, and then we have the inner product itself, so we'll have a lambda j and the inner product of xi with xj. Now if you have a question as to why can we pull this lambda j out, I mean, is it on the bra side or the ket side? Well, what you can think of is, you can write down this product here as you can pull the lambda j into the ket and just multiplies the ket vector. And then, when you take the inner product with xi on the bra side, then you can pull the lambda j completely out of the inner product. And because it's on the ket side, it doesn't change. It doesn't get complex conjugated. Or if the Dirac notation is a little too, if you don't like it, you can go back to the standard vector notation, which we used in the previous proof. Alright, so now we've got another equation 4. And comparing 3 and 4, we see that the left-hand sides are the same. So from 3 and 4, we must have the right-hand sides being the same, because the left-hand sides are the same. So we have lambda I xi inner product with xj is equal to lambda j xi inner product with xj. And now we can bring them to the same side. Therefore, lambda I minus lambda j times the inner product of xi with xj is equal to 0. Now we are told that lambda I is not equal to lambda j. Therefore, you can divide by lambda I minus lambda j on both sides, and that leads to xi, the inner product of xi with xj is 0, i.e. xi is orthogonal to xj. So the two eigenvectors corresponding to different eigenvalues of a Hermitian operator are orthogonal. Okay, now this is quite an important result, because it's something which you will use extensively in quantum mechanics when you have wave functions, eigenfunctions of the Hamiltonian, and if these eigenfunctions correspond to different energies, different eigenvalues, or different momenta, then you know that these eigenfunctions will be orthogonal to each other. Yeah, so this is something we're going to be using quite often in this course, and in fact much of physics. Now the question which you should have at this point is, what about the case lambda I is equal to lambda j? Yeah, and this is a very good question, because this proof breaks down if lambda I is equal to lambda j. If lambda I is equal to lambda j, then this term here in the parenthesis is 0. If that's 0, then we cannot say that this term also has to be 0. It could be anything, and this equation would be satisfied. So this proof doesn't hold for this case. Now here's where I'm going to be a little bit fuzzy, because um, I'm okay. First of all, the full proof for this particular case is not in Riley, Hobson, and Benz, but you can find it in other slightly more advanced texts, or at least more complete texts. In general, let's say you have k. So let's say that there exists k degenerate. Now when you have the eigen values being equal, we call these degenerate states, degenerate vectors. We have k degenerate eigen vectors x n, where n is equal to 1 to all the way to k. All right, so that is lambda 1 is equal to lambda 2 is equal to blah 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 is equal to lambda k. These are degenerate states. Now if I took a linear combination of those xn, so consider a linear combination of the xn, let's call this x prime, and this is equal to some linear combination n is equal to 1 to k, and we'll call these coefficients cn, and then we have the xn. Now this linear combination, any such linear combination, is also an eigenvector of the operator. Let's check. Okay, so we'll operate with A on x prime, and it's A operating on this sum. Now this is a linear operator, so we know what it does. A linear operator operates on each term in the sum, and so we can pull the sum out. N goes from 1 to k. Now it doesn't do anything to the constant here. This is a scalar, Cn, so it operates on the xn. But we are told, in fact, that the eigen values for each of these eigenvectors they are all equal. Let's just call them lambda. So A operating on each of these xn, this gives us lambda times xn. So this then is equal to the sum, n goes from 1 to k, cn lambda times xn. We can pull the lambda out and put the rest in a parenthesis. And this stuff here is simply x prime, so it's lambda x prime. Therefore, any such linear combination is an eigenstate of A, or eigenvector. I use the two, we can use the two, they are synonymous, so we could either call it an eigenstate or eigenvector of A with eigenvalue lambda. Alright, so the eigenvalue is unchanged. Now here's what we're going to do. So the proof we have above, this proof here, doesn't say anything about the orthogonality of these particular states, because they are degenerate with each other. So I don't know if these xn's are orthogonal to each other. But what we can do is, if they are linearly independent, and this is the if here, so let's put down that the proof on previous page says nothing about the orthogonality of these degenerate states. Yep. But, and this is the key here, if they are linearly independent, then we can use Gram-Schmidt orthogonalization to make them orthogonal. In fact, to make them orthonormal. Okay, so, and this can be done. Now it turns out, and this is the part which I'm not going to prove here. If any of you want to know the proof, I will tell you where you can find it, or try and give you an outline of it. But it turns out that for any Hermitian operator, these these degenerate states will always be linearly independent. And because they will always be linearly independent, you will be able to form orthogonal in fact orthonormal functions from this set using Gram-Schmidt orthonormalization. And therefore the result here, where we said that the eigenvectors of a Hermitian operator corresponding to different eigenvalues are orthogonal, this result in fact can be generalized to the eigenvectors of a Hermitian operator in general, whether they are whether the eigenvalues are different or equal to each other. It doesn't matter. If the eigenvalues are different, then the orthogonality follows from this proof. But if the eigenvalues are the same, so if you have degenerate states, then you can make these eigenvectors orthogonal using the Gram-Schmidt process, which you have seen in the previous recording. Okay, so I'm going to put this here. This implies that the eigenvectors of a Hermitian operator are or can be made orthonormal. Okay, so they either are orthonormal if their eigenvalues are different, or they can be made orthonormal using Gram-Schmidt if their eigenvalues are the same. Now this is great, because what this will tell us then is that the eigenvectors of a Hermitian operator are rather special. They are or can be made orthonormal. Now if you are working in a space of n dimensions, then the matrix form of the Hermitian operator will be n by n, and we will see it will have at the most n eigenvalues. In fact, it will have n eigenvalues. They may not be different, some of them may be the same. And these n eigenvalues will then be associated with n orthogonal uh, eigenvectors, and these eigenvectors will be able to be used to form a basis for this space. So the eigenvectors of a Hermitian operator become a natural means of developing a basis for a space. And coming back again to quantum mechanics, what this means then is once you have found the eigenfunctions of a Hermitian operator like the Hamiltonian, then you can use those eigenfunctions as the basis for your space, as long as you've got them all. For example, once you've solved the hydrogen atom problem and got all the functions, there are an infinite number of them. In fact, there are an uncountably infinite number of them. You can then use those eigenfunctions as the basis for any hydrogenic problem because those functions form a complete basis for that space. And any other wave function for a hydrogenic atom, you put an electric field on, you do whatever, you put a magnetic field on, any other wave function will be representable in terms of those eigenfunctions of the Hamiltonian for that hydrogenic problem. Okay, so this is quite an important result with quite significant consequences. I'm going to pause this here and come to the next topic soon. Alright, so I just wanted to write down some questions, and here they are. So here's question 1 for you. We have looked at the case, properties of Hermitian operators. Now I'd like you to show that the eigenvalues of an anti-Hermitian operator are imaginary. Okay, so this is a proof which is, try and do it first. The proof is in Riley, Hobson and Benz, but try and work it out on your own using the same kind of ideas we have used for Hermitian operators. Now, if you manage that, and I hope you will, then show that the eigenvalues of a unitary matrix have unit modulus. Now, remember, we are treating matrices and operators as kind of interchangeable. You get from one to the other by introducing a basis. You get from an operator to a matrix by introducing a basis. So you could also look at this as a unitary operator, in which case you'd have the operator forms of these equations. So if A matrix X vector is equal to lambda X, and if A inverse is equal to A dagger, that means it's unitary, then show that lambda, the modulus of lambda squared, the modulus of lambda, that squared, yes, is equal to 1. Now what this means is that lambda then is equal to e to the I theta, right? So you're going to have complex, particular kinds of complex numbers on the unit circle as the eigenvalues of a unitary operator. Now here's a sub-question. Now we know that orthogonal matrices or orthogonal operators are kind of a special class of unitary operators which are real. So A would be orthogonal if A inverse is equal to A transpose. So that means A is real. Now what would happen there? Okay, so try and work off the case. So what would happen there? Now these solutions are in Riley, Hobson and Benz, but try them out yourself before you go any further. Okay, so what's coming next? Now next what I'd like to do is two main things. We're going to look at normal matrices. We've looked at Hermitian operators. I've given you exercises to look at the case for anti-Hermitian and unitary and orthogonal operators. But now let's look at the more general case. Now we're getting more general by looking at what happens if you have a normal matrix. Alright, so that's going to be in a separate part because this is getting a bit too long, so I'm going to stop this here.